Welcome to Brain Vision.
Okay, in this problem we have a non-relativistic particle with mass. We are asked to find the wavelength of this particle in terms of its mass and its kinetic energy. And once we have this expression, we're asked to find specifically the wavelength of an electron with 800 eV of kinetic energy. The equations we'll use is the definition of a de Broglie wavelength in terms of h and momentum, Planck's constant h. We also need the simple definitions for kinetic energy and momentum. All right, let's jump into it. So starting off with our definition of the de Broglie wavelength, h over p, we're going to replace the momentum with something involving m and k. To do that, we will look at our definitions for k and p, and we'll combine them to get k equals p squared over 2m. We can do this by replacing v, by solving for v in one of these cases, the velocity, and then combining it with the other equation. We end up with this new expression for kinetic energy in terms of momentum. And in one more step, we can then express p, momentum, in terms of kinetic energy and mass. P is equal to 2mk. So we can take this momentum, plug it into our definition for de Broglie wavelength. We get h over root 2mk. So that's our expression involving m and k. Now we can get a specific actual result for an electron with 800 eV of energy. You can take Planck's constant to be 6.626 e to the negative 34 joule seconds, divided by a big square root, 2 times the electron mass of 9, which is 9.1 times 10 to the negative 31 kilograms, times 800 electron volts. And then we need to convert our electron volts into joules using 1.6 times 10 to the negative 19 joules per EV. And once we do this calculation, we end up with a value of 4.34 times 10 to the negative 11 meters, so very small. And that's it. We have the wavelength for an electron. We have an expression relating wavelength to mass and kinetic energy. Thank you.